Thank you, Paula. So hopefully most of you guys stayed from the last talk Miguel gave. I'm going to follow on with that and dig deeper into integration with Spark and kind of what we're doing to make it more GPU friendly. In case you weren't here the last talk, so I'm Tom Graves. I work at NVIDIA. I'm a senior software engineer working on Spark there. I am also a Spark PMC, and I've been working on Spark since before it was an Apache. So a long time, yeah. So to recap on RAPIDS, I think most of you actually were here, but I wasn't sure who would come. So RAPIDS is a GPU accelerated data science library. It has multiple parts. You can do the whole end-to-end from the data preparation to machine learning to visualization. cuDF is the CUDA data frames library. It lets you do the analytics, so you can do joins and filters and that sort of thing. cuML is a machine learning library. cuGraph is a graph processing library. And then RAPIDS also uses an arrow memory format, which lets you easily communicate with some of the deep learning libraries, so PyTorch, MXNet. And then there's a visualization library, cuXFilter. Okay, so now into a little bit deeper. So Miguel hit kind of what XGboost was. So I'm going to talk about how it works with Spark and what we're doing to accelerate it. So you can use XGboost with Spark now. There's a library, XGboost for J and Spark. It allows you to train on multiple GPUs, so you can scale your data and do bigger things. It works right now with Spark 2.x. You can go download it and use it. But of course, we want to make things faster, right? So we've been making it run on GPUs. So it's been running on GPUs for a little while now, but we've been trying to accelerate it further and just make this better. So as of now, you can actually do it on a multi-node and multi-GPU. And the way we do this is it actually leverages a library NVIDIA writes called Nickel. And this is a communication library that can work multi-node and multi-GPU. And under the covers, it figures out the best way to do things. So if you're using like a high-speed NVLink between your GPUs, it will utilize it. And if not, it will fall back to use PCIe or internode, just sockets. And so this is great. We've got this working, and the performance is much better. Here's just an example of what we've seen. This is a very preliminary results. I actually need to update this slide. But this is running on Google Cloud. And here you can say we're using 15 CPUs, and comparing that against the GPU. And the max tree depth is 8 and 20 here, you can see. And the accuracies you're seeing are the same. And we're seeing 6.5 to 7.5 speed up, roughly. And again, these are preliminary numbers, and they've actually gotten better recently. Okay, so it's running, XGboost is running fast on GPUs. That's great, right? But what do we want now? Well, we kind of want, and this is where RAPIDS comes in, we want the whole end-to-end to be better, right? So usually when you're doing some machine learning, you do some ETL first. You load your data, you do some massaging, maybe get rid of some bad values, and then you're going to send it into your XGboost. So we want that whole thing to be better. So we want to look at the ETL side of this, and how do we make that faster on the GPU? And this is basically where RAPIDS comes in. And so the cuDF library specifically on RAPIDS is a CUDA data frame library. It lets you do data science operations. So you can do your filters, your sorts, your group bys. It can also load data from your various formats directly. So you can read your CSV data, your Parquet data, your ORC data. And when you read that, it goes directly into GPU memory. So at that point, you're already on your GPU. You don't have to do any copies from your CPU after you've massaged your data. And so, as Miguel had said, cuDF is C++. You get very good performance. You use CUDA and C++. It's also an Apache Arrow memory compatible format. This lets you pass it between frameworks. And it stores everything in a column major format. So the GPU likes to work in columnar. That way it can parallelize everything and go very fast, right? And it also allows you to do a large amount of data. Okay, so what does this mean for XGboost? So recently we basically made XGboost run on cuDF. At this point, it's mostly reading the data. So even though cuDF has support for different things like joins and filters, currently we're mostly concentrating on reading the data as a first step. So XGboost runs on Spark 2, which doesn't have great support right now for columnar data and making your own kind of plugin. So we've kind of hacked together some APIs, which we kind of modeled off after the dataset and data reader APIs. So we created a GPU dataset and GPU data reader that essentially call into cuDF to read the data, and that pulls it into the GPU memory, and then you can use that directly to go from columnar to the D matrix format, which is a row-based format, and then XGboost takes that D matrix. It does require a memcopy because you're reading it in and then converting it to this D matrix formats, but it's much faster still than reading it from the CPU. Okay, so now we have that, and this is available now, and this is some of the performance numbers we're seeing from it. So this is the training classification. It's on 17 years of mortgage data, which is about 190 gigs, so a medium-sized data set. And here we're comparing both AWS and an on-prem cluster. You can see we're getting some pretty good numbers. So on AWS, we're comparing 4 R5A 4X large servers with 16 cores each to one P3 16X server with 8 V100 GPUs. And in this case, we're seeing 34X speed up. And that's going from like 7.5 hours down to 15 minutes or so. So you can see a huge benefit there. And if you look at the cost side, right, we're still seeing a 6X cost improvement. So we get both. We have some on-prem servers, which are some Dell PowerEdge 740s. They have 16 cores each, and in this case, we're using 2 of them. And then on the GPU side, we use the same 2 servers, but they had 4 T4s. The T4 is a little bit lower end model for data science. And here we still saw a 9X speed up and a 5X cost saving. So I don't remember what the times were. So it's still like 6.5 hours down to 40 minutes. Okay, so let me give a quick demo. Let's see if this works. So I kind of cheated and I pre-recorded a demo. So
That's a plan
I didn't trust the network. So stay with me here a minute. Okay, so I'm going to start. This is actually where you can go get XGboost. So there's a RAPIDS AI Spark examples GitHub page. And this has all the information you need to get started. So, and we have different types of applications. So you can run Scala, you can run Python, you can run on-prem if you want, and then you can run in all the major cloud service providers. So you can run on EMR, SageMaker, Databricks, GCP. And there's some notebooks here. So there's a bunch of examples, instructions on how to get started. And there's some specific APIs. Okay, so here's just when you can go to some Databricks specific instructions, and this will walk through exactly how to set it up on Databricks, and it will give you the requirements. So in this case, we support Databricks 5.3, 5.4, and 5.5 runtimes. The Databricks ML GPU runtime libraries, they already come with XGboost, so there's a little bit more setup just to kind of copy our version over that, but it's pretty straightforward, really. And we have instructions and actual notebooks to help you set this up to make it even easier. And then it kind of walks you through the whole process, and it's easy to use. And it goes into some of the XGboost specifics, like if you want to change the parameters and try things out, you can. So this is just the initialization notebook where this is actually doing the work. You can manually do this too, but essentially you have to download 3 jars and set up some init scripts which do the copy over the Databricks version. And then in the end, it has instructions here that tell you how to use that init script and kind of restart your cluster. And then at that point, you're all ready to go. And so here's an actual notebook using XGboost. You'll see that we're using the 5.5 library here. And it has a description, and we're loading. Here's where we're loading the XGboost libraries. And so one of the main parts here on the ETL side is that we have this GPU data reader API. So it's kind of modeled after the Spark data reader API, but it has a limited functionality. It doesn't give you the whole data reader or data set API. We'll be looking at adding that later in like Spark 3.0 when we can support the columnar better. And so here we're just kind of, it has information on how to do the CPU version and what the differences are as well. But here we're loading some CSV data. We're setting up the schema for it. Here we have some of the parameters for XGboost. Again, you can go modify those as you will. And so here we're actually setting up the Spark session. Again, it talks about differences in the CPU version. And we're getting into the actual data reader part. And so here's actually where we instantiate the GPU data reader. You have your normal options, your headers, you can pass in your schema and set up your features. And this is, again, just talking a little bit about the CPU version. And so we're actually reading the data here using the reader. And this is underneath is going to use the RAPIDS readers, the CSV reader in this case, and pull it directly into GPU memory. As far as the XGboost side, here is where we tell XGboost to use the GPU. So the only difference really is going from this HIST to GPU HIST. And then you'll want to change your number of workers, right? Because with CPUs, you'll have 12 or 16, and on the GPU, you may only have 1. This example, we just used 1. But other than that, those are the only parameters you have to change to XGboost. And so here we're getting into your regular XGboost code. If anybody's familiar with it, this looks very familiar. We're setting up our classifiers, setting our labels, and then setting our feature columns. So the feature column bit, actually, this is a new API, and we're working on getting it in the Spark community now. It just makes it a little bit easier to do multiple features. And so here's the code. So we just have a benchmark object to time things, right? And then we do the fit and the train. And we already ran this here, obviously. So after that, we can do the transformation and evaluation on it. And this is all just regular XGboost code. And you can kind of see your results with your probabilities and raw predictions and such. And then the end here, we're just going to save this model to disk. We're going to end up loading it back just to see the results on the transform again. And so the write here actually goes through the CPU, QDF. Currently in our library, we haven't integrated with the new RAPIDS CSV writer. So they're working on writers as well, so you can go directly from the GPU to CSV or Parquet or ORC. I believe the CSV one is implemented, and they're working on the Parquet and ORC one. Okay, so back to the slide. Okay, so we're working on XGboost and RAPIDS. We're also working with the community on this so that everybody can get it, and it's not something that is only in our repo. So with QDF integration, we have an issue open. You guys can go follow it if anybody's interested. We're also working on some other features, such as external memory support for the GPU. So this will basically allow you to kind of spill memory to the CPU memory. So right now, there is some support for extra memory, and it's just using compression on the GPU. So as you read the data, you process it, and then you can kind of compress it. But as soon as you run out of that GPU memory, it will still fail. This feature here will allow you to spill the CPU memory to do a lot larger data sets on a small number of GPUs. You will probably see some performance impact, because you have to spill, but it's better than just crashing sometimes. Okay, so if you want more information on this, so we just released a blog on this, I believe yesterday, maybe Tuesday. So you can go to the newsdevelopernvidia.com and read that blog. It has some more information, some performance numbers, and you can also go, so in the demo I showed the RAPIDS AI Spark examples repo. You can go there to get started, try it out, and then you can also submit an issue there. So please go try it out. If you run into issues, let us know. We'll be glad to help. Okay, so we're going to talk about now how Spark 3 empowers GPUs. So we've done we've done a few of these and we're working on some of these. So GPU scheduling, we're working on a stage level scheduling and then columnar processing in Spark, which will let you utilize GPUs. Okay, GPU scheduling. So what's the problem here? So right now you can use GPUs in Spark, but Spark itself doesn't know about them, right? Spark doesn't schedule on them. You just kind of have to figure out a hack to make this work, right? I've seen many people on Yarn, they have a dedicated queue with GPU nodes, and they'll come up with hacks such that you acquire a percentage of the resources, and that means that you get a percentage of the GPUs. So if you have 4 GPUs on a node, for instance, you might acquire a container that has 25% of the CPU in memory, and that means that I get 1 GPU. And that's very brittle, right? I could easily accidentally launch, well, I want 6 executors on a node that has 4 GPUs, and then things fail, right? And especially on a multi-user queue, you can have somebody kind of mess things up for a lot of people. And so Spark itself doesn't know about it, and that becomes a problem, right? So it makes it difficult to use. So what we've done is in Spark, we have added accelerator-aware scheduling. And this is actually all checked into Spark 3.0 at this point, so you can try it if you want to build Spark yourself. And it adds scheduling and awareness to Spark for any sort of accelerator that has addresses. So in our case, we're concerned with GPUs, but you could also do it with FPGAs or any other accelerator you may have. And so what this has done is it allows you in Spark to request your executors with a certain amount of resources. So normally in Spark you ask for, I want X amount of memory and a certain number of cores. And then on the task side, there is a configuration that says how many CPUs a task wants. And it defaults 1, most people leave it at 1. But with the resources, we basically give you all the same functionality. So you can ask for executor resources. You can specify what you want for your driver's resources. If you happen to need a GPU on your driver, you can do that. You can specify how many resources each task needs. So if my task needs 4 GPUs, you can specify that. There are some limitations depending on what cluster manager you run on. So currently we support Yarn, Kubernetes, and standalone mode on Spark, but each one has its different uniquenesses. And some of them, for instance, like Yarn, it will not tell you what GPU it's allocated. So you can say, I want a container with 1 GPU, and it'll give you that container, but it won't give you what GPU address was given with it. So ideally, like on Yarn, you're running in isolation as well. So you ask for a container, and it gives you a container, and you can only see whatever GPUs you've asked for. But to work around that, we've also added the ability to discover resources. So when you launch an executor, it will run a script that you've provided to discover what's there. And that way Spark can use those addresses to schedule on and to ultimately tell you what addresses to use. We also have, so obviously we have APIs to get the resources you need. So there's a task API, there's a Spark context API, where after your task is launched, you can look, okay, what addresses did I get assigned? And I want to pass those addresses into TensorFlow or whatever else you're using. And so like I said, this is actually checked into Spark 3.0 now, and you can try it out. So here's an example of a Spark shell, and all the configs you kind of need to use this. They're a little bit long, but they're generic. So in this case, I'm doing GPUs, but if you just switch GPU out for whatever accelerator you want, all the same things happen. So this first one, we're asking for a driver resource. We're asking for 1 GPU. The second line is the discovery script. So as soon as your driver starts up, it's going to run the script and figure out, okay, what actual addresses do I have? And then after that, we have the executor configs. So again, you specify your resource amount. In this case, I'm asking for 2 GPUs. So the top line, I'm asking for 2 cores, and I'm asking for 2 GPUs for this. So I'll be able to run 2 tasks. Sorry, the fourth line is the amount of tasks, number of GPUs per task. And then the last line is just sending the discovery script with. And so inside of Spark, we actually have an example discovery script, and that should work in 99% of the cases if you're using an NVIDIA GPU. So you should just be able to use that in most cases. If you have a specialized situation where maybe you don't have isolation or something, you might have to write your own GPU to properly assign GPUs. So the API. So this is a task API that you can use to get what you've been assigned. In this case, you just use a task context, and you can look at the resources, and that resources gives you a resource information object back. And the main thing here of interest is the address, right? So I want to know, am I on address 0, 1, 2, what have I been assigned? And you can pass that into TensorFlow or whatever other framework you're using. Here's the driver side API. So Spark Context has a resources option, returns a map of resource information. And so you can do multiple resources as well. If I need both GPUs and FPGAs, Spark will do that for you, and you can look and see what you've been allocated. In this case, you've been allocated address 0. And so the full flow of this, if people aren't familiar with Spark. So a user would submit an application with the configs that I specified. Spark starts the driver, and then it uses those configs to pass those on to the cluster manager. So for instance, on Yarn, it will say, hey Yarn, I want a container with this amount of memory, this amount of cores, and this amount of GPUs. Yarn will give you back a container. Spark will launch that container. I don't have a pointer. And when the executor starts, it will run that discovery script, and it will discover, hey, I've got a GPU, address is 0, for instance. It sends, Spark sends that information back to the driver, and it registers with the driver. And the driver can then use that information to schedule tasks on. So all the executors register, it knows what addresses each one has, and then Spark will, when it starts a job, so you run an action, it will start a job, split it up into stages, and then it runs a task, right? So the task has a requirement. In this case, in my example before, I said I want 1 GPU per task. And so when the scheduler goes, it will find a node that has 1 GPU, 1 CPU, and then schedule it to that, and it will send the address along with that. And so when your task gets started, it can use that task context API that I showed you to find out which GPUs it should be using. And it can, again, pass those to TensorFlow or whatever your favorite algorithm is. So we've also modified the UI to hopefully make this a little bit more obvious to users what you've been allocated. So right now, it's in the executors UI. You do have to push, is this a pointer? Oh, that's not, sorry. So the UI is getting very large and cluttered, so we've added checkboxes. So you have to check the box to see what resources you've been allocated. In this case, there's a node there that has 2 GPUs, addresses 0 and 1. Standalone mode, if you're familiar with that, has some more UI options as well, because you have to configure that slightly different. Okay, so if you want to find more information on this, so the JIRA Spark 24615, it went through the whole SPIP process, was approved, and like I said, all the code's been checked in at this point. If you use it and find any problems, let me know. There's user documentation, and again, if something's not clear, please file a JIRA, let us know. And so some other things going on related to this, we're also working with Berkeley Rise Lab, which kind of runs our CI/CD and Jenkins instances, to get actual GPUs installed on those machines, and that way we can run it through CI/CD nightly, make sure we haven't broken anything. NVIDIA was gracious enough to give them GPUs to use for this. So there's also actually a lot of other Apache projects that were interested in this. So okay, thanks. Something else related to this, so we're working on fractional support. So right now you can ask for whole integers, basically. So I can ask for 1 GPU, 2, 3, 4, but you can't say I want 2 tasks on a single GPU. And so we're working on that. There's actually a pull request up for it, and it'll be in 3.0. Okay, so stage level scheduling. So what is this, right? So most of the time when I'm running a machine learning algorithm, like I said earlier, I want to do some ETL. So I read the data, do some massaging of it, maybe get rid of some bad values, and I send it into my machine learning algorithm. So most of the time when you do that, the containers you need to do that are quite a bit different. All right, on my machine learning side, I probably want a GPU, or my TensorFlow wants. On the ETL side, I don't. Right? And maybe if I'm doing a lot of data, I'm doing terabytes of data, I need thousands of containers. The resources used for that are completely different than the ML side. So stage level scheduling is trying to solve the problem that I need 1 container size for 1 stage, and then the next stage I need a different container size. And so to solve this, we basically have a proposal. So Spark 27495 is a proposal which has actually passed to implement this in Spark. And so how we're proposing to do this is you specify the resources needed for a specific RDD. And that RDD will end up being put into a Spark stage. I'm not sure who's all familiar with Spark, but when you run an action, you run a Spark job. That Spark job gets split up into stages, and those stages are based on a shuffle boundary. And so when Spark goes to schedule, it looks at what RDDs are in that stage, and it will look at the resources you've associated with them to decide what kind of containers, what size of containers you need. To do this, we do require dynamic allocation because obviously we have to give up the containers we had and get new ones, because none of the cluster managers that I'm aware of support changing container sizes, right? And that's pretty hard when you have something like memory. So right now, the first implementation, at least the proposal, is to rely on dynamic allocation. Currently, Yarn has dynamic allocation. Kubernetes doesn't. They're working on it. As soon as they have a shuffle service, it should work there as well. And then, so we're modifying Spark, obviously, to work all the way through to your cluster manager to request the correct ones, and then it will schedule on it. Kind of like I talked about before, it will know what those tasks in that stage need and request containers of that size and schedule them accordingly. And so here's an example of what the API might look like. Like I said, this isn't completely done yet. So we're creating a new resource profile, is what it's called. And in there, you give all the requirements you need, very similar to what you do now in your Spark job or with the resource scheduling. So you can specify your executor requirements, memory, cores, GPUs. You can specify your task requirements, and again, all the options, your startup, your discovery scripts and such. For now, we're going to limit the types of resources and such that you can actually do through this API to like memory, cores, and resources, but it can be extended later. And so once you have your resource profile, like I said, here's an example where I'm making an RDD and I'm doing a map partitions, and this might be something look a lot like what you do if you're calling into a ML algorithm, TensorFlow, again, whatever it is. And then, so after your map partitions, you say this with resources, and you pass in the profile you created. And so that will associate that resource profile with that RDD, and then the scheduler can use it later to schedule on. And in this example, you'll see that we're creating a Spark task context and getting the GPU addresses again and passing that into our ML algorithm. Okay. So the next topic, so I'm going to talk about how Spark SQL works with GPUs and how we're kind of integrating it with RAPIDS. So as of before our SPIP, Spark didn't do much columnar processing, right? It did support some in like ORC format, Parquet format, and in transferring data in Arrow to Python. So there was some columnar in Spark, but most of the processing in Spark is all row-based, right? You're iterating through a set of rows. So that doesn't work very well with GPUs, which wants columnar. And so there's a bunch of people actually kind of working on this recently. You can go see these three things are talks that people have given. The vectorized R execution. In the Spark Summit in US, they had two talks, making nested columns first-class citizens, and the vectorized query execution at Facebook. And both of those were using vectorized or columnar format to accelerate the processing. So lots of people are kind of seeing benefit of doing this. And like I said, the data frame API is a row by row basis, and so we can't take advantage of columnar. So to kind of help this and be able to run Spark on GPUs, we had a JIRA and proposed this idea to the community, Spark 27396. And what it did was, it's trying to be non-invasive at this point. So we basically modified Catalyst to put in a plugin point. And maybe I should back up. I don't know who's familiar with Catalyst, but basically the data frame API and the dataset API use an optimizer that's called Catalyst. And Catalyst creates a plan for your jobs. So if you go in, do a filter, a join, a group by, etc., Catalyst under the hood creates a plan for this. And then it goes through multiple stages. So you have your logical plan, and then it will go to an execution optimizer, and then you'll get your final plan, physical plan to execute. And so we put in some plug-in points in the Catalyst to be able to take this plan and change it. So we can take it and see, okay, this is a group by. We're going to change this to be a GPU group by. And we've added in everything we need to be able to convert from rows to columnar, send it to the GPU, and then come back again. And like I said, we're working on this. The SPIP has passed in the community, so they like the idea. We're going to be putting up design and code here shortly. So how does the RAPIDS fit into this? So with those plugins, we're able to modify Spark and have a plugin basically that calls into RAPIDS to do GPU work. Again, it requires the Spark 3.0 plugin we put in. We're really trying to keep the user from having to change their code. So this is why we use the data frame and dataset API, mostly concentrating on the data frame API. Because users can still write their Spark data frame API, and under the covers, it just knows, oh, I can do this on the GPU. Let's go use RAPIDS and run this. To run this, all you need is a jar, well, 2 jars, a plugin jar and a QDF jar, and then set one config. After that, the plugin figures out, okay, is this an operation I can run on the GPU? If it is, it can modify the plan, and if not, it will still fall back to the CPU version. So you can run this plugin and actually have everything run on the CPU if it doesn't know how to do those. And we'll continue to add functionality, which will get more to run on the GPU. Obviously, more we can keep on the GPU, the more performance benefit you get from it. And like I said, it handles the row to columnar and back again. So here's an example of how this will work. You'll see that we have just the config and the jars, and then you launch your shell as normal. So here's, if anybody's familiar with the Spark UI, there's a SQL tab up there where you can go look and see what the plan actually looks like. So this is an example of running with our GPU plugin. You'll see here that we use the GPU shuffled hash join at the top, and then we actually fall back to the CPU. So it converts it from columnar to row. We do a normal shuffle, and then it's going to do a sort on the CPU side. And this is a very easy query. So we've done some benchmarking on this, so it's very early, but our benchmarks look pretty good. So this is a TPCH query 4, and we're doing 100 gigs of data on GCP, 5 workers, N1 high mem 16 machines with 80 shuffle partitions. And you'll see that we're getting a 3.55x speed up. And so the speed up is definitely very dependent on the query. It also depends on the amount of data. Like Miguel was saying, the GPU works better on a larger amount of data within reason. It has to fit on the GPU, obviously. So the more data you can throw at it, actually the better results you can get. Okay, so some future enhancement that we're planning on doing on the plugin. So we haven't released the plugin yet. We're still working on it. We want to make sure that it's usable and stable and such before we release it, possibly early next year, first or second quarter. But so we have some operations available. We want to add more operations, make it more functional. We also want to put in an optimizer. So like I said, right now it's smart enough to know I can do this operation on the GPU, and if it can, it will do it. But there's lots of times you don't necessarily want to do it, right? If you have a small amount of data, it doesn't make sense because you have some overhead of copying to the GPU, running, and then copying back. So we want to put an optimizer in there to help figure out when it should run and when it shouldn't. We want to be able to handle larger data, so the spilling stuff similar to XGboost. Right now, if it runs an operation on the GPU, it has to fit in memory. And so we want to be able to handle spilling to handle large amounts of data. There's new hardware coming out, like GPU direct storage, which will help accelerate this even further. So GPU direct storage lets the GPU read directly from like NVMe drives. We're looking at RDMA and other shuffle improvements. So if you're using a lot of GPUs, it's a whole lot faster to go GPU to GPU for shuffle rather than having to go back to the CPU across the network. So we're investigating some of those. And then a couple other ones supporting UDFs. So right now, if a user writes function, we don't know how to do that. There's a couple options, like Miguel had mentioned, to do that. And then ultimately, we also want a better exchange format for Spark to go to ML. So something like Arrow possibly. But we want to investigate that and see if we can get something into Spark to make that easier. And I'm going to skip the demo. And That's right. And so just to summarize, so Spark 3.0 empowers GPU apps. So we've done multiple things and are working on. So the GPU scheduling, stage level scheduling is in process. The columnar processing plugin is there, and our plugin with Rapids is coming. For XGboost Rapid Spark, this is available now. Again, go download it, try it out, let us know how it works. Like I said, we've been seeing some great performance improvements from this. And thank you.
Thank you.
And don't forget to fill out your session.
Plenty of time for questions. Who has a question?
Hi. First of all, congratulations for these changes to expected for Spark 3.0. In March, I attended the meetup, Spark meetup in Barcelona. There was Aldrin Carauder. Okay. I asked her if there was something like this in plan. She didn't know. I'm happy then this is going to happen.
Good.
And my question is about the proposed changes to the Catalyst API for the columnar processing. Did you check if this is going to have impact for those Spark application still running on CPUs? Because there are still a lot of use cases. There is no payload expected.
No, no, it's purely just a check. If you've actually filled in the config, then it will call something. Otherwise, it's, yeah. There's lots of, so Catalyst itself had other plugin points where you can put your own optimizations and such in, and this is basically just another point to do that. And so the overhead is nothing if you don't configure it. Yeah.
Thank you.
I have another. Just on the side. Hello, again. Congratulations, pretty good, pretty nice talk.
Thanks.
Is there any hope for Mesos?
So there's a Jira open to support like is GPU scheduling on Mesos. It's up to somebody in the community to take it. I don't know about Mesos, which is why I didn't do it. I don't have that background. But if there's anybody interested in your field, free to work on it.
Okay, because Mesos at least shows the GPUs there and supports some of the scheduling on the GPU side, but
yeah, I knew that, and that's why I filed the Jira. But I don't know enough about Mesos to do it myself without spending a lot of time. So,
okay, thanks.
Yeah.
Thank you. This is really exciting. Just a quick question. I noticed that when you're doing a lot of the demo and stuff, it was using the Scala API. Is that because the PySpark API can deserialize the data and put it back to the driver?
So as long as you're using the data frame API on PySpark, you don't actually go into Python.
Okay.
It's only when you do a UDF. So that's another benefit of the way we did it with the data frame API. It works in Scala, Java, and Python under the hood as long as you're staying in that data frame API. So our plugin and such will work no matter what.
So but then I guess the next question would be for the resource allocation, would the data have to be required to be in Apache Arrow data format?
For what specifically?
To be able to essentially push data if you want to leverage the QDF data?
No, so QDF knows how to read ORC files and Parquet files and CSV files, and it actually knows a couple others, as you mentioned, JSON. They're adding more. So the arrow format is only like if you wanted to do something QDF and then give it to your ML algorithm that knows how to read that. And so that's where I mentioned it'd be nice if Spark had more of a standard there. There's a bunch of frameworks that at least have went to Arrow, right? I think TensorFlow supports it. And so it'd be nice to have that for users in Spark to say, hey, give me an Arrow buffer. That way I can pass it straight there without having to write it to a file and then have like TensorFlow read it back.
Hi.
Hello.
Thanks for the talk. I have a question about stage level scheduling. So if I understand it correctly, and correct me if I'm wrong, so if you have one stage that requires no GPU, like you're doing ETL in a no GPU stage, for instance, and then you have a next stage that requires a GPU, it will actually allocate new nodes from, say, Yarn or whatever that have GPUs?
Yeah.
And then, okay, so what happens with the shuffle data? So you have shuffle data that comes from the first set of nodes, and it needs to move to the second set of nodes. But ideally, of course, you'd like to shut down the first set of nodes when you no longer use them because your second stage is using GPUs.
Well, so you're not shutting down the node, you're giving back the container. And for dynamic allocation, it relies on an external shuffle service. So like on Yarn, the external shuffle service is ran on the node manager. So even without the stage level scheduling, right now if I run a task, it's going to write out to disk, and that node manager is going to serve that out. So I can shut down Spark containers now. So there's no difference there.
I'm sorry. My this is because of my Databricks background, where the
right.
entire thing gets shut down.
So,
But
standalone mode depends on what cluster
manager
manager you're used to, right? Some of them support dynamic allocation, some of them don't.
Thank you.
All right, I think we have time for one more. Yes, one more. Let's do it.
I actually had two questions, but let's get started with one. So, a very great talk, a lot of exciting work. So one thing I'm confused with is, there seem to be some operations that require GPU specific kind of a support, like the translation, the catalyst optimizer that would do the group by translation would use a GPU group by, you said, right? So, so how does this work? So do you have to translate function by function and provide implementations like average and all the different mathematical operations? So if yes, how many operators are supported, and what is it like? Will every operator will it have to be supported separately?
Yeah, so in our plugin, the user doesn't have to do any of this, but in our plugin, we basically have to do that. We have to have a mapping. So for a join, for instance, we have a function on our plugin side that says, okay, I can do a join. Well, what type of join is it, right? Is it shuffle hash join? Is it sort merge join? Okay, I can do some of these, and then that one I can do on the GPU. These other ones fall back to the CPU. But essentially, yeah, on our plugin side, we have to know almost, every operator, do we support this or not?
There's a fallback.
Yeah, yeah. So anything that we don't know about or can't run on the GPU, if there's a data type we don't support, okay, we just do it on the CPU side.
All right. Thank you very much, everyone. Thanks so much for attending.
Thanks.
Please